to discuss on the basic state space uninformed searches in AI. As we know that artificial intelligence is related to making the machines do the things that human beings are doing at present. We encounter in an AI technique that we have a state space search in which we have to find our particular solution. We represent this with the help of a graph or a tree. At the end of this session, student will be able to demonstrate various state space uninformed search algorithms. By these algorithms, we are going to see the second part of our AI technique. Our AI technique has three parts. The first one is a start state, then a control strategy that takes us from the start state to the goal state, and the third is your goal state. And therefore, this control strategy is a state space search. We go for uninformed search because this particular searches will not be requiring our total graph right in advance, but in going to search and visit the particular nodes, we shall be encountering our goal by visiting the most promising nodes from all the nodes available in our state space chart which we have drawn. The various algorithms involved with uninformed search, or what we call as the methods that we go to search where information is not available or informed to the particular user of the system well in advance. We have three algorithms: a breadth first search, a depth first search, and a depth first iterative deepening algorithm. In the breadth first search, we traverse a graph in a breadthward motion. Rather than going directly into depths, we go layer by layer and encounter visiting all the nodes in a particular layer before going to the next layer. We use a queue to remember and to get the next vertex to start the search when a dead end occurs in any iteration. We all know that the queue works in first come first served basis. So the breadth first search algorithm for this particular graph traverses from A to B and then to E to F first, then and then to C and G. Lastly, we go to D. So this is the way in which we are going to traverse by encountering the breadth nodes A, B and C before going to the next level. What are the rules to be followed and understood are: the rule 1, visiting adjacent unvisited vertex, mark it as visited, display it and insert that particular vertex in a queue. The second rule is, if no adjacent vertex is found, remove the first vertex from the queue. And the third rule tells us that you have to repeat the rule 1 and 2 until the queue is empty and we have visited all the nodes. For our graph, we shall first initialize the queue where the queue is set to be empty. Then we decide upon starting from visiting the particular graph from the visiting starting node and mark this node S as visited. We then see unvisited adjacent nodes from S. There are 3 nodes, but alphabetically we will choose the node A, mark it as visited and enqueue it into our queue. As we have seen now, A is the node which is now present in our queue. Next, we go to see from A the unvisited adjacent nodes from S, and here we encounter it to be B. We mark it as visited and enqueue it. So now our queue has, first A has been pushed in our queue, then now B has been pushed into our queue. Next, the unvisited adjacent node from S is C. So we mark it as visited and enqueue it. So now our queue has first A has entered, then followed by B, then followed by C. Now we see that S is left with no unvisited adjacent nodes. So we dequeue it, and when we dequeue it, first we find A because first come first served, and therefore A comes out from our particular queue. From A we have D as unvisited adjacent node. We mark it as visited and enqueue it into our particular queue. Now the contents of our queue is the first element being B, then C, then D. At this stage, we have no unmarked or unvisited nodes left. When a queue gets emptied, we are done now. What is the problem with this breadth first search is that we have to store all the nodes, and this occupies a large amount of memory. And it is also robust and will definitely give us a particular solution, and it is a promising algorithm, but it takes a large amount of time. The next algorithm we go for is depth first search, where we traverse a graph in the depthward motion. Here, instead of queue, we use a stack to remember and to get the next vertex to start a search when a dead end has occurred in any iteration. We know that the stack goes by FIFO. However, last in first out is going to be our orientation for our particular stack. And here we see that our graph can be represented as we have shown here. The rules to be followed are: visit the adjacent unvisited vertex, mark it as visited, display it, push it in the stack. Then the rule 2 is, if no adjacent vertex is found, pop up a vertex from the stack. So push and pop are the operations that are used to implement this particular stack. It will pop up all the vertices from the stack which do not have adjacent vertices. For the rule 3, I repeat rule 1 and rule 2 until the stack is empty and we have dealt with all the nodes that are present in our particular graph. So you initialize this stack as I am showing you here in step 1. Then I mark S as visited because that is my starting node and put it into the stack. Explore any unvisited adjacent nodes from this S. We have 3 nodes here and we can pick any one of them. For this example, we shall take the node in an alphabetical order. Now mark A as visited and put it on the stack. Explore any unvisited adjacent nodes from A. So both S and D are adjacent to A. But we are concerned for the unvisited nodes only and not the nodes that have already been visited. Now from A we visit D and mark it as visited and put it now into the stack. That is, I am pushing it to the stack. Here we have B and C nodes now which are adjacent to D and both are unvisited. However, we shall again choose in an alphabetical order and we choose B. We mark it as visited and put it on the stack. Here B does not have any unvisited adjacent nodes, so we pop B from the stack. Popping is done in the last in first out fashion. We check the stack top for return to the previous node and check if it has any unvisited nodes. Here we find D to be on the top of the stack now. Only unvisited adjacent node is from D is now, which is remaining C. So we visit C, mark it as visited, and put it onto the stack. As C does not have any unvisited adjacent nodes, so we keep popping the stack until we find a node that has an unvisited adjacent nodes. In this case, there's none, and we have kept on popping until the stack is empty. The algorithm which follows still the depth first search, but has added to it the iterative deepening to search for the most promising nodes from those that are available, is termed as the depth first search with a limit and an incrementally growing limit. I call that as an iterative deepening depth first search, and therefore I could evaluate this particular method to find out, yes, it is complete. It has a time complexity of O of b raised to d. It has a space complexity of O of d, where d is the depth and b is my branching factor in my particular graph for a particular node under selection. I do a comparison between this branching factor to be 2, 3, 5, 10, 25 and 100, and I find a ratio of iterative deepening depth first search algorithm to depth first search algorithm, and I get the ratios of them to be 3 to 1.5, 1.2, 1.08 and 1.02. I could go to apply these particular algorithms for the forward and backward. I can use the depth first search, the breadth first search, the depth first iterative deepening, all the algorithms, and I could go in a bidirectional fashion from the start to the goal node. All these methods are but slow, and therefore they are called blind because we are not considering any sort of estimate for us to select a particular good node and a more promising nodes. However, though these algorithms are slow, we use these particular algorithms as the first type of algorithms to get our particular goal and compare between how our estimates are going to change. A solution to get the more promising nodes and to get our result at a faster rate and save our memory is to add guidance, which is called a heuristic estimate, where each node has now a particular value, and as per the values of the next node that we could select, we would select the particular next node that leads us to our particular goal or tells us how far we are from the particular start and the goal. So we go for informed searches rather than uninformed searches. For our references, we have used. Thank you.